Okay, today we're going to look at the final type of bonding that you need to know, and that is the bonding within metallic substances. And here is a picture that gives you an idea of how the bonding occurs. You've got lots of metal positive ions. You can see they're all arranged in neat layers. And between those positive ions you have electrons. And those electrons are free to move throughout the structure, the giant metal lattice structure. So now, although these are ions, because the electrons that are here have come from the outermost shell, we've effectively got a giant lattice of metal atoms. And as I said, it's those outer shell electrons that are free to move and are delocalized throughout the whole structure of the metal. You've got to remember or bear in mind that this arrangement continues in 3D, and there are millions and millions and millions of metal atoms in a metal structure. Now we've got opposites here. We've got negatively charged electrons delocalized and a positive nucleus for the metal atoms. So there is a strong force of attraction between the positive and negative charges, as we've seen before. Opposites attract. And this attraction between the opposites, electrostatic attraction, again, but in this instance, it's called a metallic bond because it's found in metals. Now, this would be one of those times in a lesson when I'd say to you, talk with your partner. Why do you think these are the case? These properties are the case for metals. Well, obviously, you won't have a partner. So what I want you to do is have a think for yourself about these points here, and then we'll talk about them. So metals have a high melting and boiling point because there is a strong attraction between the nucleus of the metal atoms and the delocalized electrons. Okay, a strong attraction always leads to a high melting point and boiling point. And remember, that attraction is over the whole lattice. It's not just in a small part of the lattice, it's throughout the lattice. So there's lots of bonds you need to break to melt a metal. And they are strong bonds. Metals can conduct electricity, and heat, because of the delocalized electrons. The delocalized electrons will carry charge throughout the whole structure of the metal. Conduction of heat doesn't quite work in the same way. The electrons don't move as much as they can when electricity is being conducted. What happens is they bump into each other and pass the heat on. But again, the essence of this, they can conduct heat because of the delocalized electrons. Now remember, malleable means that metals can be hammered into shape. And it would be worth you having a diagram of this type in your notes. Look what happens when you put a force on your metals, on a metal, then the layers of atoms slide over one another and they'll just slot into new positions in the lattice. A slightly distorted shape or change shape lattice, but they will still slot into position. You can see the arrangement here is exactly the same as the sort of arrangement that you get after it's been hammered. So key explanation, or key words to get into your explanation, is that the metal is made up of a layer of atoms, and when you hammer a layer of atoms, then they slide over one another. Now we also need to know about alloys. You've done a little bit about this in the dim and distant past. But we need to remember, what is an alloy? Well, an alloy is a mixture of metals. Why are alloys more useful than other metal, or than the metals themselves? And you'll cover this again actually in year 11 a little bit. But it's because typically they are stronger, they are harder, or in some instances they do not corrode. We need to be able to explain why alloys are harder than the pure metals themselves. And again, we use a sort of model to help us. And again, it would be worthwhile if you make a little sketch of this sort of picture for your notes. What goes on here? Well, if you look carefully, you can see the main metal here, which is the grey atoms, are no longer in layers. So having smaller, or indeed larger, atoms of another element within the metal structure disrupts the layers. And when you disrupt those layers, they can no longer slide over each other. So there's your explanation why are alloys stronger than metals, because the different size atoms disrupt the layers so they can no longer slide over one another. Okay, you can read that as well as I can. Now, there's a summary worksheet that I'm going to include on here, and I also want you to complete a Google Forms quiz on types of bonding. And then the next thing for you to do is the stuff that's actually on the next slide here. So you just simply need to go onto the presentation and look at nanotechnology or nanoscience and work through the questions on the presentation there. But remember, for the quiz you're about to do, that if a substance contains a metal and a non-metal, it has ionic bonding. If it contains non-metals, and non-metals only, then it will have covalent bonding. Mostly simple molecular, but watch out for the few exceptions, which have giant covalent structures like diamond, graphite, and so on. And if it is just a metal, then it's going to have metallic bonding. Okay, on the last little quiz you did about molecular substances, quite a few of you got wrong the first couple of questions. For molecular bonding, it has to have only non-metals in it. Okay, so I'll be posting the remaining lessons very soon.